Hi, I'm Jared Goldberg. I'm a terminal-age main sequence grad student entering my final year in the physics PhD program at UCSB, working with Lars Bildston trying to understand red supergiant envelopes and their explosions. Because I'm going to be talking in a session on instabilities later about our 3D work, I think it would be interesting and fun to talk about a project we did on exploding pulsating red supergiants, and the references I've given on the title slide. Red supergiant stars typically explode in type 2p supernovae. 2 because there's hydrogen, and p because there's a distinctive plateau that lasts for about 100 days kept hot by hydrogen recombination. Now, there's a degeneracy between different families of explosions that could produce very similar light curves and velocity evolutions, particularly on the plateau after the first 30 days. That is, lower mass, more radially extended stars with lower explosion energies, like the blue lines in the figure on the right, can produce similar light curves to higher mass, higher energy, more compact star explosions, like the green line. Because of this, a progenitor radius detection is crucial, both in terms of actually seeing the star explode and understanding which stars explode, but also beyond that in terms of breaking the degeneracy, constraining the radius, and thereby constraining the ejecta mass and explosion energy. However, the concept of a singular red supergiant radius for a given star is complicated by the fact that these stars, many of them have been observed to pulsate up to 30% of their radius, with periods of hundreds to thousands of days, as seen in the lower right-hand plot from M31 from Monica's paper in 2018. Because these pulsations happen over the timescales of hundreds to thousands of days, but it only takes a single day for the core collapse explosion to happen, the density structure should be locked in at the time of death. Moreover, the explosion shouldn't really have a preferred pulsation phase. It could happen at any point, compact or expanded. But the pulsation phase, because of the impact on the progenitor radius and the density profile, could affect the supernova emission. In order to model this, we evolved an 18 solar mass star in MESA up until the end of core carbon burning. We then calculated the eigenmodes of the pulsation using the code gyre, and took the velocity eigenmode and injected it as a kick into the stellar model at different times, with amplitudes tuned to get realistically large pulsations, so we weren't concerned with mode growth, rather just getting the structure right. We then allow the star to ring from the time of injection to its eventual core collapse, and because we inject the pulsation at different times, we get core collapse at different final radii. We then proceed by chopping out the core and putting a bomb in the model and exploding it with the MESA to Stella pipeline that was developed in the MESA 4 instrument paper. So what did we learn? Well, first of all, explosions of fundamental mode pulsators agree pretty well with our expectations just for bigger and smaller stars. So explosions near pulsation maximum, like the yellow and purple lines, will produce brighter explosions, and near pulsation minimum, that's radial minimum, like the teal lines, will produce fainter explosions than the dotted line, which is the explosion of the unperturbed model. The scaling also agrees pretty well with the Popov scaling, or with our scalings from our 2019 paper, as seen in the lower right-hand panel of the lower right-hand plot. In addition, the plateau duration is more or less independent of the progenitor radius, which is what you'd expect for a nickel-rich supernova like the one we have here. So we also exploded our models pulsating in the overtones. And when we do that, because there's a node in the displacement, it actually looks like a less dense star on top of a more dense star near pulsation maximum or radial maximum, compared to the fundamental mode, which is less dense and shallower everywhere. Now, this different density profile causes different light curves. So as you see deeper and deeper into the star, shown in the upper right-hand panel, the photospheric overhead mass coordinate, as you see deeper and deeper in, you probe what appears to be a bigger, brighter star, brighter explosion at first, but then you look in and see a more compact progenitor. So the overtone exploded near the maximum will be brighter and decline more rapidly compared to the fundamental at the same radius because of this different density structure. The density structure matters. In conclusion, For pulsations primarily in the fundamental mode, bigger is brighter, and the plateau luminosity of the supernova scales simply with the radius. The overtones are a little bit more complicated because of the different density structure. Therefore, further variability studies are going to be important in determining how much of an uncertainty this adds to the progenitor radius information we extract from HST pre-imaging, and also how we use that information to interpret supernova data. We also, in this study, have not explored how pulsation phase impacts the shock breakout and shock cooling first 30 days of emission, and part of that's because we don't really necessarily trust the outer fluff of 1D red supergiant models, so there's a lot of interesting work to be done there as well. Thank you.